Hi, I'm Emma Heller. Welcome to Lab 3. In this lab, I experimentally measured the magnetic fields of a bar magnet using a magnometer application on my cell phone, and then I used GlowScript to write a code that represented the magnet in the magnet's magnetic field that it actually represented. So some of the topics we covered were magnetic fields, and then we actually saw that the bar magnet acts as a magnetic dipole, and finally we covered Biot-Savart's law, which refers to the electric field due to current. However, it's actually applicable in our lab because we had to compare our measurements that we found to the distance dependence predicted by the equations for the on and off axis magnetic fields, and that was actually derived from Biot-Savart's law. So I found the magnetic moment in my lab to be 5.063 amps meters squared, and then the B net experimental at 45 degrees off axis to be 1.688796 e to the negative 4 teslas, which I'll later compare to my B net I obtained from my computational model. So the setup was really important in this lab because we had to compensate for Earth's magnetic field, and we did this by placing my phone where the X component of the magnometer app was 0, and this means that my phone was aligned with Earth's magnetic north and south magnetic axis, which is different from the geographic north and south poles, and that's why we couldn't just use a compass. So we then placed the magnet along the east and west axis, so the magnetic field of the bar magnet was orthogonal to Earth's magnetic field, and that way it would not contribute to our measurements. And then we also had to make sure that there was no nearby electrical equipment, magnets, or anything else that could have affected these measurements. So I then had to identify where on my phone the magnometer sensor was located, and as you can see, after going through the steps, I found it in that corner there. And then once the setup was complete, I was able to find the distance dependence of the magnetic fields of a bar magnet, and I then repeated this for multiple magnetic field values. So here are my measurements that I found for each of the magnetic fields. The graph plots the ln of the x component of the magnetic field versus the ln of the distance, and then the slope of the line of best fit gives us the n value, and the y-intercept is actually equal to the ln of k, which we can use to calculate the magnetic dipole moment. So the magnitude of the magnetic field due to the bar magnet is actually proportional to some constant k, times r, which is the distance, to the power n. And since I expected the magnitude of the magnetic field to decrease with distance, my n should actually be a negative number, and I found that to be negative 2.3504 because that was the slope I had in my last slide. And then that was close to my estimated value of negative 3, so I was able to set this equation equal to the equation for the magnetic field dipole on axis, since bar magnets are magnetic dipoles, like I said in my introduction, and then I derived this equation from for k. So then I could rearrange the equation to equal the magnetic dipole moment, and then once I solved for the value of k, I plugged this in, and then the magnetic constant was also plugged in, and then I solved for u, and I found u to be 5.063 amps meters squared. So then in the second part of the lab, I found the magnetic field at the 45-degree axis of some distance d, and I just put in my values, as you can see there, and then my B net was automatically calculated for me. And I also corrected my By component for the Earth's magnetic field. So for the coding portion, I first created a magnet at origin, and then I added a function to solve for the magnetic fields. After that, I created 6 observation locations, 2 of which are on axis and 4 of which are perpendicular axis. And then next I created the magnetic fields using the magnetic fields function I had made earlier, and after that I just created the arrows to represent the magnetic field, and finally repeated steps 4 through 5 for an observation location that was 45 degrees from the axis. So here's my model. As you can see, the white cylinder is the magnet, the blue arrows are the magnetic fields at the perpendicular location, the orange arrows are the magnetic fields on axis locations, and the green arrow is the magnetic field 45 degrees from axis. And I think it's interesting to note that the on axis was actually double the perpendicular magnetic field, but it's opposite in direction, so that was really interesting. To compare the value I got for magnetic fields computational to magnetic fields experimental, I used percent error, and this percent error is very high, likely because the experimental had a z component that contributed to the overall magnitude, whereas the computational model did not have a z component at all. So to answer the what if and whys, if I had not oriented my experiment to compensate for magnetic north, then the Earth's magnetic field will superpose with the bar magnet's magnetic field and then produce a net magnetic field which would have altered each value that makes up magnetic field, including magnetic dipole and the constants K and N. And then if I was to stick two identical magnets together, my measurements would have doubled because my magnetic moment would double. So, in conclusion, I observed that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction, but as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. Thanks for watching.